Hello. Okay, dumb intro done. So let's do kind of a last video in this series of 3 videos, kind of looking at quantification of complex traits. And so for this one, we're going to actually transition to a different type of a complex trait. So up until this point, we've been talking about continuous traits, these quantitative traits. So the kind of the trait value can be along a spectrum. Think about human height, weight, things like that. And different experimental strategies by where you compare that trait value between individuals of some relatedness, whether that's parent to offspring, monozygotic twins, dizygotic twins, things like that. And you end up with kind of a plot of these data. You can estimate a slope of a correlation coefficient, or you can estimate the correlation coefficient, which is the slope of the line of correlation, so on and so forth. So for this one, we're going to talk about discrete traits. So discrete traits are complex, but they're not continuous, right? Okay, so they're complex in that they're still, just like quantitative traits, they're regulated by many factors. Okay, really in the same way that continuous traits are. So they're regulated by multiple genes, possibly by multiple alleles of multiple genes, regulated by the environment, regulated by an interaction between the environment and the genes. So they're still very complex in the way they're regulated. However, they're discrete in that they're almost, you either express the trait or not. Okay, so you can think of these as binary. Okay, 0 or 1, right? So what are examples of discrete traits? So it turns out that a lot of human diseases are discrete traits. They're very complex. They can be regulated by many different genes. They can have a substantial environmental component, but they're still very discrete. You either have cancer or you don't. You either are diagnosed with Alzheimer's or you're not. Okay, that's the kind of threshold we're talking about here, or at least we'll get to this word of threshold a little bit later. So I think another good example of this would be something like heart disease. Okay, so again, you're either diagnosed as having heart disease or not. And now maybe that's an oversimplification of things, and I think there is a little bit of oversimplification going on here in terms of trying to make a sort of distinction between a discrete trait and a continuous trait. It's entirely possible that there are sort of varying levels, varying severity of heart disease, but we're trying to make this kind of distinction a little bit, okay? Because this ends up with a different strategy with these twin studies, okay? So, but just like with heart disease, so just like some of the other continuous traits, there's a genetic component and an environmental component. So you can think of there being genetic risk factors. Okay, things that are maybe outside of your control. So if you've got a family history of heart disease, I know that my family does, that means there's probably some sort of genetic risk factor that's being passed down from generation to generation. Okay, but there's also, you can think of things like environmental risk factors. And these would be things that are maybe to some extent within our control. So things like diet, kind of the nutrition of what you eat, physical activity, exercise, and then a bunch of other lifestyle choices. I think smoking would be like an environmental factor that plays into this. Okay, so it's still a very complex disease, complex trait rather, but we kind of view it in more kind of discrete terms. Either you have heart disease or you don't have heart disease, right? Okay. So, now importantly, you can still use this monozygotic versus dizygotic strategy to unearth or kind of tease apart these genetic from environmental risk factors in this case. Okay? But what this is going to do, and I'll go ahead and kind of erase this and kind of reset this a little bit, is this is going to then introduce us to a different term, or a new term that you need to know. So the term in this case is concordance. Okay, so concordance is defined as the frequency that both twins Okay, and this can be either monozygotic or dizygotic twins. Okay, so again, we're not comparing like a trait value. Our trait value here is 0 and 1. It's this binary discrete trait. So we're not looking at height, we're not looking at weight, we're not looking at body mass index. We're looking at whether you have heart disease or you don't. Okay, so then this concordance is the frequency that either of these twins, so frequency that both twins, whether it's monozygotic or dizygotic twins, have heart disease, right? So we're not kind of measuring a slope here. Okay, so really the simple way to kind of think about this is how often do both twins show the trait. That'd be a really informal way to kind of think about what concordance is or what it's measuring. Okay, so concordance, just like heritability, is on a scale of 0 to 1. Okay, so 0 would indicate that. So if you ask the question, how often do both twins show the trait? If the answer is 0, that would mean they show that none. They show the trait. They both show the trait none of the time. Okay, if it's 1, then they would both show the trait all of the time. Okay, and so then the extension of this then is this would then be, in more kind of formal terms, no concordance. And by extension, not heritable. Okay? Whereas, again, if the concordance value is 1, both twins show the trait all of the time, this would be full concordance. And highly heritable. Okay? So this is this idea of concordance. Okay? So then how does this idea of concordance fit in? Again, I'll just keep kind of putting it over here. This idea of comparing monozygotic twins versus dizygotic twins. How do we get to this point with this concordance value? Okay, so a little bit of a reset. So the broad strategy in this case is to compare monozygotic concordance with dizygotic concordance. Okay, so you're going to get two values out of this. And so instead of, again, the parallel would be comparing the correlation coefficient that you get from studying continuous traits of the monozygotic to the dizygotic. But in this case, you're really just getting one value out of that, which is a concordance value. But you're still comparing monozygotic to dizygotic in this case. Okay? And so the way to think about this is that if the monozygotic concordance is greater than the dizygotic concordance, again, so this means that more often both monozygotic twins show the trait than dizygotic twins show the trait. This then indicates higher heritability. Okay, so in this case, in the same kind of strategy here, if the monozygotic concordance is the same or similar to the dizygotic concordance, this indicates no heritability or very low heritability. Okay. So there is again a way to quantify this, and I'm not going to go into sort of how this equation, how they came up with this or how it's used really. I just want you to focus on the sort of qualitative aspects of it. But the actual equation, the heritability, we'll call this the narrow sense heritability, is the monozygotic concordance is the dizygotic concordance subtracted from the monozygotic concordance, all divided by 1 minus the dizygotic concordance. Okay, but kind of really focusing on this part of this equation that's in your textbook is really the key part of this one. Okay, so as this number gets bigger, So again, if this monozygotic concordance is much larger than dizygotic concordance, then this h squared gets bigger. But again, as this approaches 0, so if the monozygotic concordance and the dizygotic concordance are the same, this goes to 0, this h squared goes to 0 as well. Okay, so you can still then measure this h squared on a scale of 0 to 1. Okay? So I want you to check out table 22.2 in your textbook. This is on page 755. Okay, so this actually lists out a number of different discrete disease traits. And it actually shows what's been done to unearth both the monozygotic and dizygotic concordance values. And so you can kind of go through that and you can get a sense for which of these disease traits may have a higher heritable component to it. There's some actual numbers to it. And you can actually look at a couple different things when you look through this table. So the first one is to look at the concordance value of the monozygotic twins alone. Okay? So even without comparing it to the dizygotic twins, and that's going to vary between sort of 0 and 1. So if you just look at the frequency with which two monozygotic twins show that trait, you can actually estimate the sort of genetic contribution and the environmental contribution based on that number alone. It's not going to be perfect. Maybe not as good as comparing the two, but if this monozygotic twin concordance is very, very low, that suggests that maybe there's a really large environmental contribution to this. So just kind of looking at the table over here, it looks like one of the lower ones is, say, Parkinson's disease. Okay, that has a monozygotic twin concordance of 0.16. That's pretty low. Suggests that maybe there's a large environmental component to this one. Okay, so the first thing you do is just look at the monozygotic concordance values. And the second thing you can do in this table is to actually compare the monozygotic concordance versus the dizygotic concordance. So then you get an even better idea of how much of that trait is regulated by, has a genetic component to it. So kind of two different ways to look at it. Okay, so this is the last video in this series. I think the next series will kind of, I'll get at, and maybe we'll post something even as soon as tomorrow afternoon. It has to do with the reading that I'm assigning for you to read tomorrow, which is looking at an experimental strategy to actually start to dive into what is the genetic component. So a lot of what we've been talking about up to this point has really just been identifying to what extent is a trait regulated by genetics or the environment. If we really want to dive into that genetic component of a complex trait, there are some distinct experimental strategies to actually do that. And so the reading for tomorrow talks about what's known as a genome-wide association study, or a GWAS. And I think I'll post a video, hopefully tomorrow, that talks about the GWAS. They've been used, I would say, very, very, very frequently for the last 20 years or so. And they're, I think, being used even more now that our ability to sequence genomes has really shot through the roof. So look for that tomorrow. Yeah, have a great rest of the week. Have a great weekend. Get outside. Enjoy some of this warm weather. See ya.